So my name is Willem. I am the CTO of Cleric. Today I'm going to be talking about our product and how we hit a performance bottleneck and how we overcame that bottleneck. And maybe there's some lessons that you can learn and apply to your AI products when you kind of plateau in performance. So let me tell you about what Cleric is and what it does. So you can think of Cleric as like an incident, like a first responder. We want to keep you coding, and we want to take some of the gunk work away from being on call or debugging production issues. So what we do today is we've got an AI agent that can trigger based on an alert. And these are typically from PagerDuty or other events in your production environment, but primarily PagerDuty. And so this agentic architecture is not that different from what you've seen out there in the wild, but the use case is kind of different, and I'm going to talk about that today. So what we do is we generate a plan, a set of tasks, and then we execute that plan. And ultimately, what you get as a user is a diagnosis or a root cause. And you get that in Slack. And of course, there's a lot of details that I'm going to abstract here that we can talk about maybe in the office hours afterwards, how we've constructed this agent, memory architectures and knowledge graphs and all those things. But for this talk, I think the key thing that I wanted to communicate is, we reduce a search space that is very large in your production environment down to a core set of findings. And we interact with many different systems and automate a lot of mechanical work that an engineer would have to do. So you are effectively staying in your flow state, in your IDE, while we take on the gunk work of investigating alerts that fire in your production environment. So typically this is not a human in the loop, it's an ambient agent. So it's not something that you're coordinating with and interacting with. You just get the results of this agent. And so one of the key things we realized was that UX aside and UIs and all the bells and whistles, the only thing the engineer really cares about is the accuracy of these results. And if you spam them with the wrong findings and wrong diagnosis, then they get frustrated. So with the obvious ideas, you just train a bigger model, and that doesn't work because production environments are quite complicated. Unlike coding and writing, where the data is available online, you can't just train it. You don't have the problem solution pairs. Even with GitHub, you've got a lot of issues and PRs that are connected. But in operational troubleshooting and some of the harder use cases, these are dynamic systems. They're distributed, they're stateful. People are chatting in Slack, or systems are coming online and offline, and you don't have the data in all cases to reproduce and train a model. So there's a lot of reasoning required and interaction with these worlds, just like with self-driving cars, and there's a lot of data that needs to be collected. So this posed a challenge for us. So we knew we needed to learn from production environments and then quickly adapt our agent into these environments to generalize it. But then we ran into a problem, and this problem was that we saw our agent fail in production, and we wanted to replicate these failures in our eval bench, and that's really how you improve its performance. And this gap between production failures, these unique ones, like this red curve going up, and what we could reproduce in our evals was just growing week on week for two reasons. One is you don't have the ground truth. Like, you don't know what the root cause is. And so we worked with engineering teams, and they'd say, well, the results look okay, but I don't really know what the answer is. I need to go investigate myself. And so that's really challenging for us. And the other one was, so then we didn't know what to build. And the other one was building these scenarios takes time. So you'd stand up infrastructure, you'd break the system in a way that you wanted to break, that replicates production. But that's, spinning up Kubernetes clusters, you're setting up Datadog, you're setting up services, you're wiring them up. It took us about a week for a scenario, and then maintaining that scenario was also like ongoing cost. And we tapped out at about 15 or 16 different scenarios, and there's about 2 full-time engineers just managing the infra. So we couldn't keep up with all the unique idiosyncratic failures in production, and we couldn't improve our agent over time. And this bottleneck was really the core to getting to extremely high accuracies with our agent. And I think a lot of folks trying to solve this problem are hitting this. And I'll show you how we approach this problem. So firstly, on the scenario creation problem, we tried a few things. The first one was the manual infrastructure that I just spoke of. So we'd stand up infrastructure, you'd basically take things like the OTel stack and a lot of these reference architectures, and you try and break them in specific ways. So maybe you're introducing like a memory leak, or maybe you're introducing some kind of like connection pool saturation problem. but it's just very, very time consuming, and it's hard to keep it in a broken state because it's so stateful. Another thing we tried was record and replay. So you'd run the agent in production, you'd see it get to a diagnosis, and then you'd capture the whole trace and you try and run that in evals. But that doesn't work if an agent in evals tries a different path than what is happening in production. So that also didn't work. Then finally, we tried mocking production APIs. So you'd have like a fake Kubernetes, you'd have a fake Datadog using an LLM, but that also doesn't work because it's non-deterministic. So if there's a failure, then you don't know if it's due to the eval bench or if it's your agent. So we took inspiration from robotics and like self-driving cars and a lot of other use cases, and we built a simulation environment, and we call the simulation environment Labyrinth. So the insight really, you don't need to perfectly replicate the production environment in order to train an agent. And so Labyrinth is our replica or simulacrum of production. And so this is an engine that for large classes of these production systems, so Kubernetes, Datadog, Loki, Grafana, we have variants that are extremely lightweight. They're 100% deterministic, and you can spin it up on your MacBook, and we can replicate those systems such that our agent can interact with them and train against them for specific scenarios in a controlled manner. So how this works is we have a base spec that we define, and this is a world, and we can have multiple of those, but currently we only have one primary one. And we have these chaos variants that we apply to that. And together we deploy that into the engine. And so that sets up the infrastructure. So for example, it'll say, Loki should have these logs for these services, or it should have these metric profiles for these services. It could place Kubernetes in a certain state. And you can produce traces in Jaeger in a certain state. And then when the agent interacts with this world, because you give it an alert to diagnose, it thinks it's actually interacting with like a real production environment, but it's actually this simulated one. And this was extremely powerful for us because now we could spin up these variant chaos scenarios within minutes, where previously it took weeks. And almost all of the maintenance now became code maintenance instead of production infra that we had to maintain. So our ability to quickly create scenarios just exploded. And also another cool thing about this system is that all the data is just in time. So you're not backfilling data into an observability system. You're responding as the agent explores the space. So you're kind of like rolling out the railroad tracks as the agent is running through a scenario. And so we took on the next problem, which is the lack of ground truth data. And the way we approach this is that if we don't have a root cause from production, how do we improve our agent? And we looked at how engineers really approach problems. So first, we were looking at this from a top-down perspective, and basically we're saying, okay, if we have an alert, how do you get to a root cause? And if you don't have that, could we go from a bottoms-up or like a decomposed perspective? And so the insight for us was really to go with a more skills-driven approach, and I'll define what I mean by this. So when you teach a new engineer how to approach a problem, you'd say something like, if you see this alert, always go and check the metrics on dashboard X, Y, and Z, or always go and look at the logs over here if there's been a recent deployment. And a lot of these skills are learned by engineers at companies. Some of them cut across companies, but some of them are unique to specific, some of them generalized and some of them are unique. And so our ability to learn these skills is important, and it improves our performance. In fact, when we looked at the metrics of our skills, and our ability to execute these skills to complete tasks in our plan. I know that's a little bit like a lot of concepts, but effectively a task is like a unit of work and a skill is our way to accomplish that. If we looked at our performance, it was tightly correlated with skills executing correctly. And so this is an unsupervised problem because we could just look at metrics that we compute based on our skills, and I'll show you some of those metrics, and then improve those metrics and then improve our performance in production. So this is a failure mode heat map. And so we built this system. It's a post hoc system that processes all of our production traces. And this is actually real production data. I think we were trying to run a Gemini model here as one of our backing models. And you can see the performance across various dimensions for various tasks. So it's very hard to see here, but these are task categories. And so I'll just read some of them. So one of the poorer performing ones is query historical CPU and memory metrics for application pods. So the agent did poorly in that specific task category. And that's across many different traces and many different environments. And so if you look at something like this, you can just eyeball it and know, like, okay, the agent sucks at this. Let's just focus on that. And so the next step is then go into Labyrinth, create a chaos spec, deploy that, and then all your attention goes towards agent iteration. And that's where you get into, okay, do we need a knowledge graph? Do we need to focus on the memory architecture? Where are the areas of innovation that we want to lean into? As opposed to spending a week just, deploying Kubernetes clusters and getting the scenario built and breaking that. So shifting to this mode gave us a lot more of a compounding effect and speed. And so I wanted to zoom into this one. This is a specific one I was highlighting. And I'll talk about some of the columns. So for example, you look at things like incorrect arguments, incorrect tools. These are things you can easily measure in production. You could look at missed opportunities. This is an example of an agent finding information. So maybe it looks at logs and the smoking gun is there, but it didn't see it. But in a post hoc manner, you can process those logs automatically and notice that the agent missed something. So it's a very powerful technique. So when we applied these two things together, we saw a real growth in our ability to cover alerts in production successfully. So this is a graph that shows this is the coverage that we have across multiple of our deployments. So when you deploy Cleric, we don't process all alerts. We process a subset and we expand that. And so the green two layers at the bottom are the ones we are successfully solving alerts based on feedback from engineers. And the red band is the one where we failed, where they know we failed. And the gray ones are the ones we're not even trying because they are out of scope for now. And so when we deployed Labyrinth and when we got to this skill learning approach, that we saw a massive inflection of performance because we could iterate so much faster, where previously it took us just a week at a time per scenario almost. And so this gave us a lot of confidence that we could expand the capability set of our agent and learn new skills and get into new customer environments safely. Okay, so almost done. And then in terms of just the impact on our development velocity, it was massive. So now our scenario creation time is down from a week to like minutes. There's almost no memory footprint. The cost is almost negligible. Most of the effort now goes to agent development versus scenario maintenance, and we also have determinism. So where previously a failure, you wouldn't even know where to start to diagnose failures and how common they are. Now we have a very systematic way of identifying the hotspots in an agent's their weaknesses, in this skill-based approach, and we can be very targeted in solving those. And I just want to give credit to the two members of our team that built the Labyrinth system and skill learning, Peter and Dan. And if you guys want to try out the product, feel free to sign up. We have a link here to the sign up or our website. And that's it.